This is a tuning fork. It has just one job, to produce an A at exactly 440 Hertz. Tuning forks produce an incredibly pure sound, making the pitch very easy to hear. Musicians use tuning forks to produce a reference pitch, allowing them to find all the other pitches without the need for an instrument. These lightweight pieces of metal are simple, but the physics behind them are infinitely fascinating. This tiny fork helps us understand the fundamental concepts of frequency, pitch, sound waves, and musical intervals, opening the doorway into the deep relationship between physics and music. Join me as we explore the science behind the music we hear. Welcome to Sound Theory Academy. I'm David, and today we embark on an exciting series of videos that aims to explore the relationship between sound and science. Be sure to subscribe so that you get all of these videos directly into your YouTube feed. We are going to look at this through both a musical and a scientific lens, focusing on the physical properties of sound that give rise to the basis of our understanding of music theory. In today's video, we'll explore the concept of pitch. We'll look at the relationship between pitch and frequency and see how all sounds are really just vibrations in the air. Then we'll dive into the idea of musical intervals. We'll see how musical intervals can be defined through these physical properties of sound, and we'll see the mathematical foundations of intervals as seen through simple ratios that give rise to the intervals like the fifth and the octave that we're so used to. By the end of this video, you'll understand how pitch, frequency, and musical intervals are interconnected and can be explained through mathematics and science. So join me as we explore the science of sound. The story of our understanding of pitch begins over 2,500 years ago with a Greek philosopher named Pythagoras. Pythagoras is famous for his contributions to our understanding of math and geometry, but he also made remarkable discoveries in the study of music and sound. One day, Pythagoras was walking past a blacksmith shop when he noticed the different tones made by the hammers striking the anvil. He observed that the heavier hammers produced lower pitch sounds, and the smaller hammers produced higher pitch sounds. This curiosity led him to amazing discoveries about musical pitch, intervals, and tuning. When we play or hear music, one of the most easily perceived aspects of sound are the highness and lowness of the pitches. Let's listen to this scale. As we move up the scale, the pitches get higher, and when we go down, they get lower. So pitch, then, is our experience of the highness or lowness of sound. It's all pretty subjective, right? If we want to get more precise about pitch, we'll have to dive into the idea of frequency. Frequency will help us explain how this guy generates an A at exactly 440 Hertz. The term frequency refers to how many times something happens in a given period of time. If that period of time happens to be 1 second, then we can use the unit Hertz, named after the 19th century German physicist Heinrich Rudolf Hertz. In other words, when something happens once per second, we can say it has a frequency of 1 Hertz. That A made by the tuning fork, the one at 440 Hertz, you guessed it, something is happening 440 times every second to make that sound. But what is happening 440 times per second exactly? It's vibrations. When struck, the tines of the tuning fork move back and forth 440 times every second, creating a pressure wave in the air that we perceive as sound. This is the essence of all pitched sounds. They are produced by a vibrating sound source. Consider the strings of a guitar or a piano. When the strings are plucked or struck, the string vibrates at a certain frequency, producing a specific pitch. Similarly, in woodwind instruments, it's the air column inside the instrument that vibrates. Even in electronic devices like speakers, the speaker cones vibrate to create sound waves. To visualize this relationship between pitch and frequency, let's take a look at an oscilloscope. An oscilloscope is a device that allows us to see sound waves. Here's a 440 Hz wave, the same frequency as the tuning fork. Notice how it oscillates 440 times per second, creating that pure A pitch. If we move up the scale, we can see that the oscilloscope starts to move faster. It's showing us the higher frequency creates more vibrations per second. Now let's look at another frequency. Here's a 220 Hz wave, which is exactly 1 octave lower than 440 Hz. See how it oscillates half as many times per second? That's why it sounds lower. And here's an 880 Hz wave, 1 octave higher than 440 Hz. It oscillates twice as many times per second, creating a higher pitch. Now that we've seen how frequency relates to pitch, let's talk a little bit more about musical intervals. Musical intervals are essentially the distance between two pitches. We typically use terms like octave or fifth to describe the interval between two pitches on an instrument, like the piano. But this conventional language, which describes intervals with words like third, fourth, and fifth, and so on, is based on an established theory of musical scales and tuning. With our understanding of frequency and pitch, we can define intervals more fundamentally as specific ratios of frequencies, which form the basis of these musical terms. The musical intervals that I mentioned a moment ago, the octave and the fifth, can both be described in basic ratios. Let me show you what I mean. Take the octave, for example. We saw that a 440 Hz pitch and a 220 Hz pitch are 1 octave apart, two A's 1 octave apart on the piano. This is because the frequency ratio is 2 to 1. Every time you double the frequency, you move up 1 octave. So 880 Hz is 1 octave above 440, and 220 Hz is 1 octave below. The 2 to 1 ratio describes octaves, but every interval has its own unique ratio of frequencies. Let's look at the fifth, one of the most common intervals in music. The frequency ratio for a perfect fifth is 3 to 2. This means that for every 2 vibrations of the lower tone, the higher note vibrates 3 times. Let's say we want to find the frequency of the note a fifth above our A440. To do this, we simply multiply 440 by 3/2. This gives us 660 Hz. So 440 Hz to 660 Hz forms a perfect fifth. That's the 3 to 2 ratio. These simple ratios help us see the mathematical foundations of musical intervals, the basis for all of our music theory. These ratios were among some of the great discoveries that Pythagoras made thousands of years ago, and they still ring true today. So to summarize, pitch is our perception of the highness or lowness of sound, and frequency can define those pitches precisely using hertz as a unit. Musical intervals like the fifth or the octave can be defined as simple harmonic ratios between two frequencies, like 2 to 1 or 3 to 2. In the next video, we'll dive into the harmonic series and overtones, which are incredibly fascinating and explain the richness of all of the different sounds we hear. Be sure to subscribe so that you don't miss any of those videos. If you enjoyed this video, please consider giving it a thumbs up. And if you've noticed some relationships between math and music in your studies, put it in the comments. I would love to read about them. Thank you so much for watching today's video, and I hope you come back and watch the next one. Thanks.